Today, we're going to talk about the properties of soils, which I can understand. You might be thinking, "Oh man, how boring!" But again, I need to point out that soils are absolutely everything for human survival. Without them, there will not be people. We are terrestrial organisms. We are based on a food pyramid that has land plants at the base, and without soils, you can't have those plants. So you should have some respect for them. Okay, people, let's learn about them a little bit. Okay, so what does it take in order for a soil to be fertile? So when we say fertile, it means good for growing plants. All right, so a fertile soil is good for growing plants, and an infertile or low fertility soil is just not really good for growing plants. Like back in the States, uh, my house that my wife and I purchased, we love to garden, but you know what? It's terrible there because we have horrible soils. They're very sandy soils that come from glaciers. Anyway, they're not good for growing. So, and there's not much we can do about it. So let's just talk about this. What makes a soil fertile? First of all, it has to be able to retain water, right? So plant roots grow down, and after a rain event, it could be weeks or even months before it rains again, and these plants need to be able to continue to access water, moisture from the soil. So it's essential for a good soil to be good at retaining water. But also, it has to be able to drain water away. So if water builds up too much in it, then it's bad for the plant roots and the bacteria that need to live in the soil. So you have to have this right balance between holding on to water, but also letting it flow through. And the other thing is you have to have sufficient aeration. In other words, it has to be possible for air, which carries oxygen, to get inside the soil. If air can't work its way into the soil, then aerobic microbes, which are important to the nitrogen cycle, and plant roots, which breathe, they respire, right? They need oxygen too, which they get through air, not through water. So it's important for soils to have aeration in order to support plant growth. So let's just get into the nuts and bolts of this a little bit. Okay, so there's two properties about soils we're going to talk a lot about. One of them is called porosity. The other one is permeability. So porosity means it's a measure of how much of the soil's matrix is occupied by basically open space, not mineral particles, but just open spaces. Okay, these pores are the spaces between the mineral particles, and it's in fertile soils we tend to find have quite a bit of this open pore space. And the reason is this is what allows water to get in and cling to the mineral particles. And it's also what lets air get in here to provide the aeration that plant roots need. So generally speaking, porosity, good. We want porosity. Okay. Now, what happens is if the pores in the pore space in this between the pores between the mineral particles become completely filled with water, we lose our aeration. We refer to this as being waterlogged. And here's the problem with waterlogged soils. Well, there's really two problems. Okay, so basically, if the pores are filled with water, that means that we can't get any air in there. Okay, and if we can't get any air in there, things that breathe air are going to suffocate and die, drown, if you will. Okay, well, what are the two things in soil that we don't want to suffocate? Well, one is plant roots. So some plants are adapted to this kind of environment. They have other ways of providing oxygen to their plant roots. Okay, they can move it down from above, but most plants can't do that. Most land plants need to have aerated soils in order to provide for their plant roots to have respiration. So when those plants experience waterlogging, the roots suffocate and die, and when the roots suffocate and die, the plants can't survive and they die. The other one is that nitrifying bacteria. Now, remember back at the beginning of the year, we talked about the nitrogen cycle, and it's really important when it comes to growing plants, right? Because this is what returns nitrogen, which is a vital nutrient. You can't make amino acids with it. And without amino acids, you can't have proteins, can't have the nitrogenous bases that make up DNA. You can't have life. You need nitrogen in the soil. And remember, the nitrogen gets in there by nitrogen fixing bacteria, bring it in, but then nitrifying bacteria turn it into a form that is absorbable by plants. Well, those bacteria, the nitrifying bacteria that make nitrogen available to plants, they're aerobic. You fill up those spaces, they suffocate and die, and now you've got a soil that can't turn nitrogen into a form that's usable by plants. And worse yet, the denitrifying bacteria, the ones that take nitrogen in the soil and return it back in the atmosphere, they're mostly anaerobic, which means they're okay without oxygen. So you waterlog the soil, and what happens is the bacteria you need to help the plants die, the ones that take nitrogen out of the soil and put it in the atmosphere, live, and so your soils very quickly become infertile. waterlogging bad. Permeability. So permeability is, you can think of it as is water permitted to flow through. Okay, so permeability is the ability of water or any liquid, really any gas too, any fluid, to move through the matrix of pore spaces. So these pores are interconnected, and permeability is a measure of how well water, and we'll just worry about water, can flow from one pore to the next. So therefore, it make it through the soil. So soils that have a low permeability, they don't drain very well, and they have a tendency to become waterlogged. Soils with a high permeability let water through very easily, but we have to be careful because if it lets it through too easily, then we don't retain water and we can't support plant growth. So good soils have a kind of an in-between permeability that they let the water through. They don't cause waterlogging, but they still hold on to it long enough to allow the plants to continue to access it. So let's just look at how particle size plays into these factors. Okay, so basically porosity, it regardless of the size of the particles, and the shape matters, but let's just consider spherical particles. Okay? So when I go from large particles to small particles, the total amount of pore space isn't going to change. But what is going to change is the ratio of surface area to volume of the particles. Okay, and so we find is that soils that are composed of large particles tend to have larger connections, right? And so that gives them higher permeability. So if I pour water into gravel, it flows through very easily. If I pour it into sand, it flows through a little harder. If I pour it into something that's even smaller than that, it really has a hard time going through. So what we find is small particles make for small connections, and that makes for low permeability. Okay. Now let's try what happens in terms of water retention. So here's my version of a water molecule. Okay, so it's H2O. If you recall from your chemistry class, water is a polar compound. It has a dipole, meaning it has a negative side and it has a positive side. The electrons spend more time over here by the oxygen because it has greater electronegativity. Not that you need to know that, but I just like talking about it because I think it's cool. And the hydrogen tends to lose out, and so this becomes a little bit more positive. What that means is it's kind of like a balloon that you rub on your head. Because it has this charge, it'll stick to surfaces through a property, if you took physics, that we call induction. Again, you don't need to know that. I just think it's cool. The point is, water molecules will stick to surfaces a lot like a balloon rubbed on your head that has an electric charge will. And so what we find is water molecules, the more surface I have, the more adhesion there is between these water molecules and the mineral grains. So the general rule is that the greater the ratio of surface area to volume of the particles, the more water I'm going to be able to retain. So if I look here and here, there's a lot more surface area here than there is over here, right? If we just measure the perimeters, we'd see there's much less surface area here than there is here. So therefore, there's much less water retention here than there is here. The point is, small particles, the smaller the particles, the more surface area, the more water retention we're going to get. Now, I love this graph here because it sort of shows how this all comes together. So basically, we're going to learn in our next lesson that humans sometimes impact soils inadvertently. And so, we drive tractors on it, whatever. If we treat soils improperly, we can accidentally increase the density of the soil, basically pack it down, especially if it gets moist and we drive on it when it's wet. We tend to pack it down and increase its density by driving out, by basically reducing the size of the pores. So basically what we find is, in order for plants to grow well, you need this pore space. You need this interconnectedness here, the porosity and permeability. So what we find is that the porosity is higher when the density is lower, all right, and the plants grow well. So you can support more biodiversity, okay? As the soil becomes more and more compacted, then I wish they'd done this the opposite way. As it becomes more compacted, as the density increases, that means the pore space decreases. That means it has less ability to support plant growth. There's less room for the roots and less ability for water to flow through, more likelihood of waterlogging. All right, now let's talk about the three main components that make up soil. Okay, so the three main components, and you definitely got to get this into your head, are sand, silt, and clay. And the difference between sand, silt, and clay is really one of size. Now, just so you know, clays are chemically different than sands and silts. But what we're really concerned with today, and in this unit, is the size. So sand particles, which you're familiar with because you've been to the beach, sand particles are fairly large, silt particles are smaller, and clay particles are much smaller. This isn't a very accurate version of it. So this might be a more accurate. If this is a sand grain, then this is a silt grain, and this is a clay particle. And for what it's worth, we see that sand, silt, and clay particles tend to be more tabular. They're less rounded, which gives them an even higher surface area to volume ratio. So let's talk about sand, okay? So sand particles of the three are the largest, and that means when you have a lot of sand, you have a lot of permeability. The openings between the pores will be larger because the particles are larger. Now, high permeability means you're going to have low water retention, but sands are more stable. So sands are harder to compress, so they give structural support to soil. So when you have sands in soil, they're less likely to become compacted and have their density increase and basically be ruined. So having sand in soils is important, but too much sand, then it just drains too well. So what we find is if the soil has a very high sand content, it drains too quickly to support most plants. After a rain event, it pretty much dries out right away. But if a soil has too low of a sand content, it tends to have poor drainage and a lack of structural support, so it tends to become compressed and waterlogged. Now, it's worth pointing out that there's very few plant species that can survive in just pure sand. Like sea oats are one of the few that can. Silt particles are just smaller versions of sand. Now sand is usually made out of a mineral called quartz, but it doesn't have to be. Silt sometimes is. So basically, sand and silt are chemically pretty similar, just silt particles are smaller. And so because they're smaller, what that means is they're going to provide better water retention. Remember, there's more surface area, so I can adhere more water molecules. But the price I'm going to pay is the openings between the pores are smaller, so I'll have less permeability. So we find that is for farming purposes, if I have to choose between a sandy soil and a silty soil, I should choose the silty soil because there is still permeability. It's not necessarily going to get waterlogged, but it's going to do a better job of holding water, which is really what the roots need. And to this end, I just want to point out the importance of silts. Okay, so when a river floods, what happens is like in a big storm event, every a couple times a year, rivers tend to flood. They did it here last year, if you recall, in the south part of Korea where there was all this flooding. Well, it's in a place called a floodplain. So where rivers are kind of have wide valleys, kind of as they get down to lower elevations, they have wide valleys. We call these things floodplains. And what happens is in a big rain event, the river overflows its banks and spreads out over this floodplain. Well, remember the depositional environment. So sands tend to fall out even in those flood events. The sand tends to just fall to the bottom of the river, but the silt and the mud tends to be suspended. Now, when the river overflows its banks, the silt it slows down because of friction, and the silt falls out. The clay particles, however, stay suspended, and they tend to flow all the way out to the ocean. So what we find is in areas where we have floodplains, like the southern part of Korea, that's really good for farming. We have these silty soils on the riverbanks, which are really good for farming because remember it is really good at retaining moisture, and also too during these flood events, there's a lot of nutrients, organic debris that's caught up in there. And so there's often not just good water retention, but there's also a lot of nutrients that get deposited in these events. And so these floodplains, although they flood, so people die sometimes when this happens. People have always wanted to farm there. From the dawn of civilization, people have farmed these floodplains because they are so fertile. And so, case in point, Mesopotamia. The Tigris and Euphrates River, which we call this the Fertile Crescent. Okay. This river valley here, these two river valleys here, flooded all the time, and they just had so much good silty soil. Same thing is true of the Nile. In fact, the Nile River is kind of interesting. The fact that we have 365 days in a year, who figured that out? The people who figured that out were the people of Egypt, because they had these things called Nilometers. And if you go to Egypt, you'll see them. They're super cool. They're basically just these wells that are on the side of the river, and you can measure the height of the water. And so because the Nile flooded every year, and this flood brought the fertile silt to the shorelines, which allowed them to have this great amount of food, which allowed them to support their civilization, they knew that you really needed to keep track. You needed a record to know. Well, for them, they wanted to have a religious ceremony to promote the river god to bring more silt. So they kept track of the water level using these nilometers. And over the course of hundreds, maybe thousands of years, they worked out that the flooding of the Nile happened on average 365 days, and that's how it came up with. Before we knew that's how long it took the Earth to go around the sun, the Egyptians figured that out by the flooding of the Nile, because it was so important to bring that fertile silt over the banks and onto their farmlands. You can tell, I think it's kind of cool. Okay, now let's talk about clay particles. So clay particles are very, very small, right? And they tend to be produced by not mechanical weathering, but by chemical weathering. So minerals called feldspar and biotite and muscovite, you don't need to know this, but these are they're a fairly significant component of igneous rocks. And when they weather, they turn into this kind of reddish material we call clay minerals, which are super small and kind of flat shaped. Okay, so they have a really large surface area to volume ratio. And as a consequence, because they're so small, clays have almost zero permeability. As a matter of fact, when municipalities want to build a lake, they have to put clay in the bottom. You put clay in the bottom, water can't get through it, and the lake will form. I talked to a guy. He teaches. As a matter of fact, he teaches AP environmental science, and he was giving a lesson that I took. And he lives in Texas, and their county paid like millions of dollars to put in this wetland that was going to be this great place for everybody to go and see ducks and wildlife could be there. Well, it turns out they filled it with water and they didn't put enough clay down, and they had to drain it out and pay millions of more dollars to bring in more clay. The point is, clay has super, super, super low permeability to the point that it just prevents water from flowing through it if it's just pure clay. So the bottom line is, too much clay in a soil means you're going to have very low permeability, which means you're not going to have drainage and you're going to have waterlogging. But don't get me wrong, clays are really awesome, and here's why. Because not only are clays very small, they have a lot of surface area, which lets water adhere. They also tend to have some polarity to their surfaces. So they tend to have an outside surface that's slightly negatively charged. So a lot of positive ions will stick to them. A lot of pollutants will stick to them. A lot of nutrients will stick to them. So in addition to having water adhere to them, they're actually able to trap nutrients and pollutants. So when clays are present in soil, it's really important, because one of the things that soils do for us is, as water percolates through them and infiltrates into the groundwater, soils purify the water. That's one of the things that soils do for us. And clay is important. If you just have sand, those pollutants just go right into the groundwater. But when there's clays present, it tends to catch them. So clay does have an important role to play here. Now, clay particles are small, so they stay suspended, like I said. So when those rivers overflow their banks, the silt comes out, but the clay just keeps on going, and it goes all the way out into the ocean and gets deposited offshore. It's the last thing that falls out. Now, it's worth noting, just like plants don't like to grow in sandy soils because there's not enough moisture, they don't like to grow in muddy soils, because when there's a high amount of clay, then there's a very low permeability. There's waterlogging, and most plants just can't handle that. Turns out most soils contain a mixture of sand, silt, and clay. And that's one of the things I'm going to ask you to do, is learn how to analyze soils to see what properties we'd expect from them. So here's what you need to know. Sand provides two things: structural support and drainage. Okay? Having sand keeps it from getting compressed and have its density increased to where it doesn't have any permeability, but it also helps water flow through. Silt is better than sand at retaining moisture, but it does reduce the permeability. It makes water flow through a little slower. Clay is great at holding on to water. So having some clay is really important for plants to have access to water long after a rain event. But even fairly moderate amounts of it, less than 25% clay, and you find that my soil's not draining so well anymore. Right? So we tend to categorize soils by the amount of sand, silt, and clay they contain. And so I want to have us learn to analyze them. So the ideal proportions for the perfect soil, this is the soil you want: 40% sand, 40% silt, 20% clay. The sand gives me drainage and structural support. The silt gives me good water retention. The clay gives me even more water retention. But if I have too much of this, then I don't get enough drainage. So when we have this proportion, 40, 40, 20, we call that loam. And a loamy soil is what you want in order to grow crops. Now, you can grow in other things, but this is sort of the best. All right. So let's just kind of look at them this way. So let's just look at sandy soil, loams, and clay. Okay. Now, there's more types of this, but so a sandy soil, you're going to have lots of aeration, right? There's lots of room to have air in there, and that means it's going to drain well, but you're not going to hold on to nutrients. You're not going to hold on to water. Okay. And it's fairly easy to work these soils to plant crops. Okay. Now let's look at a clay soil. I'm just going to skip over here. Well, there's not much pore space. There's not very good aeration. There's not very good drainage, so it gets waterlogged. They're great at holding on to water, great at holding on to nutrients. It's really, really hard to farm in clay. So loam has sort of the best of everything. It has good aeration and good drainage, has moderate water retention, moderate water holding ability, nutrient holding ability, and workability. So loams are really what we're shooting for when we have agriculture. Okay, don't freak out, but now we got to learn how to use a soil triangle. So, and these are a little bit tricky, so you're going to practice a bit. So the idea is I have three axes altogether. So this axis here is the silt axis. This is the sand axis and the clay axis, and these numbers are percentage. So here I have 0% silt. Here I have 100% silt. Here I have 0% sand. Here I have 100% sand. Here I have 0% clay. Here I have 100% clay. So the way I use this is if I want to look at, say, let's say I have 20% silt. I go to the silt axis, I go to 0, I come to 20. Now here's where you can screw up. You got to keep this in mind. Now what I do is I go like this. Notice right now I'm going parallel to the 0. This is the 0 silt line. I'm going to go to 20% silt, and I'm going to follow a line that parallels the 0 axis. So everywhere along this line here is at 20% silt. Everything along this line here is at 30% silt. Everything along this one here is at 70% silt. Same thing works for sand. So if I come over to here, here's 20% sand. Everything along this line here, which is parallel to the 0% for sand, everything along this axis is 20% sand. So if I was to go here, what I've got is I have 20% sand, and I have, this is parallel to this, so that's 60% silt. So if I have 60% silt and 20% sand, that's 80%. How much clay must I have? Answer, 20%. So I'm going to go here, and I look over here. Notice this axis here is 0% clay. So from here, 20% sand, 60% silt. And if I go across, I see, yep, 20% clay. So let's just look at this. So I have a soil that's 15% sand, 60% silt, and 25% clay. How would I categorize? What would I call this? So what I do is I'm going to go over to 15% sand. So here's sand. I'm going over to 15%, and I'm going to draw a line parallel to its 0 line. Okay, so everything along this line here, 15% sand, 60% silt. So I'm going to follow, here's 0% silt. I'm going to go up to 60% silt and draw a line at 60 that's parallel to the 0 for silt. So this line here, okay? Now notice that I already know where it is. I don't really need to draw that there. They've already intersected here. It's a silty clay loam, we call it. But to verify, I'll just say, well, it should be 25% clay. So if I follow the line parallel to the 0 clay axis, I come over here and I see I'm at 25% clay. All right, thanks for watching this. I think that's all I've got for you here. No, wait, one more. Okay, we'll try one more. Okay, your turn. How would a soil be categorized if it's found to be comprised of 50% sand, 20% silt, and 30% clay? So I'm just going to wait for you to try to figure this out on your own. So just look on this right here and try to figure this out. 50% sand, 20% silt, 30% clay. This is me waiting for you. Okay, find 50% sand. Okay, draw your line parallel to 0. Go to 20% silt. Yeah. Okay, so here's what did you come up with a sandy clay loam? I hope you did, because look, 50% sand is here. So it's either going to be a sandy loam, a sandy clay loam, or a sandy clay. Then I'm going to go to 20% silt. So here's silt, here's 20. Now I'm going to draw a line parallel to the 0. And the two things intersected right here, 50%. They intersected right here. And if I go over, I see that's 30% clay. Okay, thanks for watching.